Welcome to another episode of AI for Healthcare. Today we will be looking into patient trial matching using deep learning techniques in the space of oncology. It is based on a fairly recent paper by two leading hospital systems and research institutes in the US, the Dana-Farber Cancer Institutes or DFCI and the Mayo Clinic. Let's start with what problem they are trying to solve. Improving outcomes in oncology trials is critical because cancer remains one of the leading causes of death worldwide. A successful trial leads to better medicine. Better medicines directly translate to improved survival rates and quality of life for patients. Everything starts with patients. Without patients, a trial cannot begin, let alone succeed. When a trial has enough patients, it can validate the utility of an intervention. If a trial is successful, it leads to better medicines, and better medicines result in better outcomes. So, if you think about it, then to continue the process of increasing outcomes across cancer types and patient populations, we need to produce more effective medicines. For that to happen, we need to run more clinical trials. And for that to happen, we don't necessarily need more patients, but better ways of finding and matching cancer patients with clinical trials. Patient participation is the foundational requirement for a trial. Let's look at how a patient journey can lead to a clinical trial. When a patient is diagnosed with some type of cancer, they generally start treatment with some hospital that would have a care team and use medicines currently available in the market. Generally, if the patient does not respond to one or more medicines already on the market, or in case of rare cancers where there are no good medicines on the market, then the patient and care team can explore options of experimental treatments available in clinical trials. However, the world of clinical trials is very different from the world of providers like hospitals. These trials are run by pharmaceutical companies or biotech companies, have a very different starting point, and use even a different system to collect data like EDC or electronic data capturing system, as opposed to EHR or electronic health record capturing system for the hospitals. So there is a bit of disconnect between the two worlds. But the sponsor of trials wants to find right patients for their trials, and the patients wants to find right trials for them. Time is of great essence here. More importantly, the trials might wait a little, but patients often do not or cannot due to the risk of disease progression. This paper is trying to connect the two worlds using AI. So the data from EHR systems can be used to match with information from inclusion-exclusion criteria listed as part of a clinical trial. At a system level, this is a many-to-many mapping problem. Any patient would like to have multiple trial options where they are eligible given their medical condition. And for any trial sponsor, they would like to have multiple potential participants. So why can't we just say the patient has disease X and the trial is looking for patients with disease X, and then do a simple join using the disease as a key? Well, it's not that simple. The disease itself can have many variations in the name, like non-small cell lung cancer can also be called as NSCLC. Could be looking for a specific stage, like stage 3A, or a particular biomarker, like ALK positive. And there could be several other characteristics defining a very specific group of patients, like N prior treatments or no prior treatments of a specific type. So it gets fairly complicated. These characteristics can be about the disease, patient demographics, prior treatments, prior medical conditions, and so on, which are often listed in unstructured fields in addition to some information being present in the structured fields. So if this problem is so important, surely many must have tried, right? Yes, There have been multiple efforts in the past decade or so, but this paper claims to offer a few unique advantages. While very few of the prior techniques are freely available, this state of the art approach is fully open source. It also aims to do a smart ranking on matched records. For example, liver related blood tests can be part of most of the trials, so it should not be used as a critical component to rank the trials. One might think, why not just use retrieval augmented generation? Store all the patient information in the vector database, then create embeddings of key trial requirements and retrieve the relevant patients. Well, they have tried RAG as well as this custom pipeline and claims this custom approach is much better. However, in general, this is the right approach. First, we must explore and rule out the computationally inexpensive techniques like prompt engineering or retrieval augmented generation before we start fine-tuning or training any models. Let's now look at how they are trying to solve this problem. We will look at three workflows. Let's start with the first one, how the trial data is prepared. So the Dana-Farber Cancer Institute has a database of trials which were run in its systems. The first step is extracting the trial ID, which can be often the NCT ID. Using this NCT ID, clinicaltrials.gov API can be queried to get additional fields from clinicaltrials.gov. From those additional fields, one specific field is of key interest, which is the eligibility criteria. It would have a list of inclusion and exclusion criteria for subjects to participate in a given trial. Once we have that eligibility criteria, a model like Llama 3.1 is used to summarize that around key attributes, creating something called as trial spaces. Trial spaces are created by focusing on cancer type, histology, disease burden, prior treatments, and biomarkers. The next thing is patient data processing pipeline. Similar to trial database, DFCI also has a patient database. Patient information can have a very long context, dozens of visits. So we need something to filter out the irrelevant information and condense the records into only the relevant bits. This is where Llama 3.1 70B model is again used in order to select only the relevant information. This is done for only limited set of records, and the data generated out of this is used as a training data for a much smaller model based on TinyBird to train a classifier. This classifier essentially performs identification of patient records into two categories, relevant or not relevant. All relevant records are selected to create the condensed medical records. We again use Llama 3.1 70 billion model on top of these condensed medical records to create a semi-structured summary of patients. This semi-structured summary would have similar dimensions, similar aspects as that of trial space, giving us information about cancer type, histopathology, disease burden, prior treatment history, and biomarker details. So at this stage, we have created patient summary and trial spaces around 5 or 6 key attributes. This is how each looks like. As you can see, patient summary has attributes like cancer type, histology, biomarkers, treatment history, and so on. In a similar way, trial eligibility criteria also focuses on these aspects. So the trial spaces have same attributes as that of patient summary, including cancer type, histology, prior treatments, biomarkers. Then there is this pipeline which actually generates the algorithm. Using the two databases produced in the prior steps, that is the patient summary and trial spaces, random pairs are created. That is, within each pair, there will be one trial and one patient record. Then Llama 3.170B model is used to determine if there is a reasonable overlap between patient summary and trial space. That reasonable overlap acts as a label of match or no match. Using this information, an embedding model is trained which can put similar data points or similar pairs closer in the embedding space and different or dissimilar data points further away from each other in this multidimensional embedding space. Once we have trained a good embedding model, using a distance metric like cosine similarity, we can find similar data points. That is, for a given patient, we can find similar trials where the patient would be eligible. Or for a given trial, we can find similar patients who can participate in that trial. When we have this matched pairs database, the cosine similarity is not a very intuitive way for clinicians to understand how much of a match two pairs are. This is where they have additional pipeline. They focus on top N results. For a case of trial, they focus on 20 top patients, and for a case of patient, they focus on top 10 trials. And then there is an additional model which is based on Roberta, and this model is fine-tuned to essentially double check the top N pairs and determine any irrelevant pairs. So at the end, we have a refined pairs of patient and trial. They have used two type of metrics in order to evaluate the pipeline. The first one is precision at K. It is a fairly common metric used in retrieval task, and as you can see, precision at N essentially determines for top N results how many results were relevant. Precision at 10 essentially means for the first 10 attempts, if there were 6 relevant records, then the precision at 10 value is 0.6. Then there is a concept of mean average precision. This focuses on quality of the ranking, meaning we do want to have relevant results early in the recommendations as opposed to irrelevant results being present in the first few recommendations. The way this is determined is at K equals to some value. For example, if we want to focus on K equals to 5, then we focus on all the records before that, calculate precision at K for each of those, and take average of all of these records. Another example would be average precision at 10. So we focus on the 10th record and all the records before that. For each record, we calculate the precision at N, where N equals to that record number. And then we take average of all relevant records highlighted in white here, giving us average precision equals to 0.72. Now, this is where it can help us understand the difference between precision at K and mean average precision at K. In first 10 results or first 10 recommendations, if 5 relevant results are present, then the precision at 10 would be 0.5. Let's consider extreme case where first 5 trials are relevant. This would give us the highest average precision of 1. On the other hand, if the relevant values are in the bottom 5, then the average precision value at 10 would be equals to 0.35. So with that in mind, let's see how the results look. They have divided results into two key categories, where they had trial enrollment data as part of the internal DFCI database, and then they had fetched some additional trials from clinicaltrials.gov. For each of the two categories, they have precision at 10 and mean average precision at 10. And for each of those, they have used the trial space alone, which is the first half of the pipeline, and the trial checker, which is additional model built to double check the records from the trial space. So trial checker is essentially trial space plus trial checker. And as you can see, the trial checker gives us much better results. What this essentially means is out of the 10 recommendations, 9 were relevant, and those 9s are likely to be ranked as part of first 9 records in the 10 recommendations. And then we have trial centric metrics. Here they have cast a wide net because for a given trial we need a lot more patients. So precision at 20 and mean average precision at 20 was calculated. So these are fairly decent results. Remember, this is all open source and this can help patients find really good trials. Now let's try to understand all the decisions they have made while choosing certain techniques as part of this system, why they might have chosen those. The Llama 3.1 model with 70 billion parameters is used in 2-3 places in the pipeline. And the reason is likely due to this was the largest open access model when the researchers started exploring this problem statement. Then while condensing the EHR information, which can have hundreds, maybe 1,000 plus data points per patient, they have used a model based on TinyBird. And this is where a lot of critical thinking must have gone in the process. They would have a bunch of options like BERT or Roberta or DBERTA. And these models are similar in many sense, like these are bidirectional encoding models, use some variation of mass language modeling. However, Roberta is a bit better and larger than BERT, and then DBERTA is even bit more better and larger than the Roberta. So it is likely that if we want to use a model for some small scale task or when fine tuning resources are very limited, we'll use something related to BERT. And if we have even more limited resources, then as in this case, they have used a variation of TinyBird would be a good start. Then if we have general NLP tasks we want to deal with, then Roberta would be a good choice over BERT. And then if you want to deal with some additional advanced tasks with long context understanding or entity recognition, then DBERTA would be a good model. So in summary, I think DBERTA would have been the best bet for them, but I understand they have likely a tight budget, which is why they might have chosen a model inspired from TinyBird. In order to evaluate the output of this TinyBird, they have chosen F1 as metric. And if you recall the TinyBird model, it is trying to condense the information into relevant or not relevant bits. Essentially, it is a binary classifier. And what we want is all the relevant bits of information being condensed and nothing left behind. So if you don't want to leave anything behind, we want to focus on recall. And if you want to get all the relevant bits of information, we want to focus on precision. And where we want both, we want to focus on combination of precision and recall, which is what they have done by using the F1 score. Then we have embedding model. Now remember, embedding model is a model which will convert the input, in this case text, into a vector of numbers. And this is done so that the input can be represented in a multi-dimensional embedding space. The number of dimensions in this multi-dimensional embedding space is equal to the model's capacity or model's dimension. So a good starting point to use any model is going to Hugging Face and looking at the MTEB leaderboard. So this is how it looks. The MMTEB stands for Massive Multilingual Text Embedding Benchmark. It's a selection of, it's a list of multiple embedding models. And as you can see, these models are capable of performing various tasks, and there are scores associated with them on each type of task. And then there is a general score which is listed here. So these are some of the top models. As you can see, this is the model they have used, which is in top 15. But this is for multilingual embedding benchmarks. What if we filter on just English as a language? All right, so this graph changes. This is the metric where we want to score maximum while keeping the number of parameters fairly low, comparatively low. So if you look at this top model, oh, there you go. This is Stella N 1.5B version 5. So this is the topmost model when it comes to creating embeddings in English language. It has better average score across all tasks associated with text embedding generation, and at the same time it has some of the lowest number of parameters, just equals to 1 billion. So that is why we chose the Stella EN 1.5B. Finally, the Roberta large base. As we just saw, the comparison between BERT, Roberta, and DiBERTA. If you have a bit more appetite for compute power and memory, then you can go for the larger models. So something more advanced than BERT would be Roberta, and a bit more powerful would be DiBERTA. And finally, we have precision at 10 and mean average precision at 10. So this was used for patient-centric tasks, and for trial-centric tasks, they had used precision at 20 and mean average precision at 20. So in information retrieval problem, these metrics are standard, but let's understand why we need them. Patients and clinicians are likely to examine only a first few results. So we need to balance the two key aspects. The precision at N ensures the top trials are relevant. If we find 10 trials, it would be good to have 9 or 10 of them relevant to a given patient. And the other metric, which is MAP at N, ensures that relevant trials appear early in the ranking. Consider an example of your favorite search engine. We want all relevant results, but even beyond that, we want to explore only first few results. This is why appearing relevant results early matters, especially in this kind of situation where finding a relevant trial can make a difference between life and death for these cancer patients. All right, so that sums up this paper. Hope you enjoyed the review. Thank you for watching.